Hello ladies and gentlemen, good to see you again. This is the 5th lab, and this is the lab which accompanies the 7th lecture in GGS300 quantitative methods for GGS. What we went over was essentially how we estimate certain parameter variables and intervals that we're interested in when sampling from a population. And this enables us to put quantitative measures on how accurate we think our estimates are. It allows us to then make estimates from the sample to the population based on some degree of confidence. And the math that we went over in the lecture, I appreciate, is challenging, but hopefully what we're going to do today in the lab is demonstrate that it's a fairly simple calculation in order to get some of those results that we're interested in. And actually what I'm presenting in this lab does actually cover most of the examples that we went over within the lecture, so hopefully that's going to make it a lot clearer for you. If you do get stuck on any of these, hopefully you'll be able to download the code, run the code, and then also simultaneously look at the math equations within the lecture, and then hopefully we'll be able to marry those two up. And if you have any further problems, then don't hesitate to reach out to me, and we can go over them in greater detail. Okay, so let's begin. I need you to make sure that you've downloaded this from the Blackboard website. Make sure that you put this code within a folder and open it from that folder with the existing data already within that folder, because we're going to need to use it later on. So the first thing we want to do is to actually calculate a confidence interval from a normal distribution. So for clarity here, we're going to do it manually. And we're going to do that because it helps us cement those equations that we went over in the lecture. So the reason why is that if you look at many of the outputs in my own papers, by the time you get to running those types of analytics, you can just select automatically for the software to basically generate those confidence intervals for you. But the problem is that you need the baseline understanding to know what those functions are going to do, and that's why we're doing it manually here. Okay, so what we're going to do is we're going to take a mean of some sample data x bar, which is 5. We're going to take a standard deviation value of 2, and then we're going to assume that there's 50 samples, so we have n equals 50. Okay, so we've entered those 3 values, and we put them into the global environment, as you see just here on the right hand side of the screen. Now what we're going to do is we're going to find the 95% confidence interval for the mean, and we're going to calculate the standard error. We're going to calculate the standard error times the z value. So what we're going to do first is we're going to get the z score, which in the lecture, we went over that kind of pretty arduous manual way of getting the z score by working out the part of the distribution that we're interested in, and then actually looking it up within the McGrew et al. Book in the tables at the back. That's fine, you just need to know how to do it. But the point is that it's much quicker for us to do it these days just using a function. So here I'm using qnorm, so we can actually have a look at the help for that. We did go over it when we were doing quantiles previously within the probability-based lecture. And qnorm, as I said, allows us to get a specific quantile within the distribution. In this case, it's returning the z value, which for the 95% interval, because that assumes, therefore, it's at 2 tails, we have 5% distributed, so it's 2.5% distributed at each end. Therefore, we need to give it the 97.5% value. So here it's 0.975. And if that's confusing, then there's an important note that we'll get to very shortly beneath. But I emphasized previously that you need to know what the function or the table you're using refers to in terms of the proportion of the values. So in the book, the Z table refers to the proportion of the values that lie between the mean value and the tail, whereas here Q norm actually refers to the whole distribution, and therefore you need to be aware of the difference, and we'll get to that in a very short point. Okay, so this produces the Z score, which is 1.96 if you round it to two significant figures. Sorry, three significant figures. The point is that 1.96 is just a figure which should just be etched into your mind, essentially, as the 95th percentile value given a particular distribution, because you're going to come across it time and time again. So eventually you will just get to know this off by heart. So we take the Z value and then we multiply it by the standard deviation divided by the square root of the sample number, so the number of entities in the sample, and that produces the standard error, and then we multiply that by the Z score, and then that produces this value at 0.554, which here we are saying is the SEZ value. Okay, so look up that function if you still need help, but that helps us just provide that initial estimate that we need to then work out the confidence bounds. So let me just recap on the lecture slides before we progress, because I appreciate that it's complicated. So we went through those basic parts, those principles of the central limit theorem. And one of the key concepts that we covered was the standard error of the mean here, so the standard deviation divided by the square root of the sample size. And using that in practice, we did carry out this example here. And it looks like a really complicated equation, but actually it's just this particular equation here. So x bar, depending on which direction around the mean you're calculating, it's just the Z score multiplied by the standard error. And that's just exactly what we calculated. So that's relatively simple in order to give us the lower bound or the upper bound, depending on which way you're calculating it. Okay, so let's just go over quickly why we use the 0.975 value again instead of the 0.95. Well, as I mentioned, R has a built-in table that produces those probability estimate values for the entire curve, but it basically means that the estimates start from the leftmost side of the curve. So you need to make sure that you take this into account. You will remember that I pointed you to this website previously, Z-Table, and they actually, in this example, use the same type of calculation. So you see here how they have the entire area to the left-hand side of the point, which is slightly different from how we've done it in the book. So it's important to know the difference. So one final point is that when you're doing these calculations, it does actually help to find the answer for the positive Z quantile first for the confidence interval. So you can do the calculations with the positive or the negative values, but it's just that it might be easier for you to grasp if you're working with positive numbers, because then you don't have to take into account what the signs mean when you do the calculations. Okay, so the point is that we got the SEZ value, and that has been saved into our memory here, 0.05, and that's the value at the 95 confidence level that allows us to understand where the upper bound sits or the lower bound sits in relation to the mean. So what we basically need to do to get the lower bound first is we need to subtract that value from the mean that provides the left-hand bound, and then we need to find the upper bound here, which when we add it to the mean produces this value. So here we go. This is the lower limit here, and this is the upper limit here, and That's essentially what we've calculated. The only difference is that here we've used a different level of confidence. So we use the 90% value here rather than 95. So that's important to note. But then we basically get an estimate of the population mean in terms of the fact that it's within this interval range that we've produced. So we think that we can be 95% confident that the population mean is within this interval, within the distribution. Okay, and being able to express values within that level of confidence is highly important. It's used throughout the scientific research areas, throughout the sciences. Okay, so that just picks up on some of those calculations that we did within the lecture. You will remember that we essentially had to use a slightly different method if the population, sorry, if the sample that we take is smaller than 30 in terms of the number of observations. And that's because over 30, we've got a large enough sample to assume that the mean that we get in the sample is broadly representative of the population. Under 30, that assumption doesn't necessarily hold. So as a consequence, for those confidence intervals, we need to use the t distribution, which here we're talking about just very briefly, but I'll pick it up again at other points during the course. So let's just work out how to do that in R. It's very simple. So we can just, again, start with a mean of 5, so x bar, which we're going to enter into the global environment. Here we go, that's 5. The standard deviation of 2, and let's say there's 20 samples. So we've inputted all of these values into the global environment. Now what we want to do is find a 95% confidence interval for the population mean. And this time we're using the student distribution. So what we do is we use the QT function, which gives you the student distribution, okay? And the Q relates to the quantile version of it. So you can look at the help menu if this isn't clear to you. What we're entering here is the probability, the p-value. So it's the vector of probabilities here. We're saying, because we're interested in the 95th percentile value, it's 0.975 for the reasons I've already given. But then also we're entering the number of degrees of freedom, okay? So that's why the degrees of freedom here are the number of samples minus 1, because that's the standard way for us to estimate that in these circumstances. Okay, so that produces the Z score that we're interested in, the Z score, and then we multiply it by the standard error, essentially. So it's the standard deviation divided by the square root of the number of samples, okay? Hopefully you can see that. And that means that we produce this SE value, and then we're able to get the left and the right-hand side bounds. So there we go, we're producing relatively sensible numbers there. So the population mean is within the interval 4.063971, and the other end of the interval 5.936029. Great, so that's for those circumstances where you don't have essentially enough data to use a standard normal distribution. So let's calculate the sample size, and you'll remember that in the lecture we did this in the final part of the session. So suppose that you want to estimate the mean yield of corn per acre to a 95% significance level. A preliminary sample, so obviously this is the same question that we covered in the lecture, a preliminary sample of 50 acres found the mean to be 74 bushels with a standard deviation of 16.65 bushels. So the question is, well, how many acres do you need to sample to be within 3 bushels of the true mean? So we have the standard deviation just here. Let me clear the environment so that we're starting fresh. Standard deviation of 16.65 bushels. We have an acceptable error margin of 3 bushels. And then essentially we're going to get the z-score for that particular confidence level. So we're going to use 0.975 again to make sure that we capture the limit at which we have a 95% significance level. So that produces a z-score of 1.96, and then we need to multiply that by the standard error and then take the squared values. So what we end up getting is 118.3265. So let's just go down and look at the math that we did within the lecture that we covered. So here is the example. Essentially, we needed to get the z-score multiplied by sigma, so the standard deviation, divided by the acceptable error margin, and then raised to the power of 2. So this was the calculation that we did, and we got 118.32, which is the same value that we got down here. Okay, and as you'll remember from the question that we covered in the lecture, we've done a two-stage sampling strategy, so we've already sampled 50 acres. So we need to subtract that from the number of acres that we've already covered, which basically means that we've got to cover another 69 acres in order to ensure that we can get a mean that we can rely on to that 95% confidence level. Okay, so hopefully you'll be able to download that code and run it, and then it will make that kind of math example that we went over in the lecture come to life. Sampling from a distribution. So now you're going to need to to import some data into R. So let's just make sure that we've got the path set up to R correctly. So we have this relatively intimidating looking piece of code, but remember that this is just Ed's quick one-liner essentially in order to get the folder path which the current script is in. Okay, so when you run this, it says okay, RStudio API, get me the source of the edit context, which is basically this script, and give me the path to it, and then take the directory name, and then let's assign that to the value folder. So when I assign it up here, you see it's in my C drive, it's in users, Edward, Dropbox, teaching, blah, 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 blah. And I just printed it to the console down here. So then you can see that it's gone all the way through my folder path to find the right one. And that's, you know, after using R for like 8 years, that's by far the quickest way to get the RStudio environment to set to your current folder. You know, you can enter that manually, which is fine, but then the minute that you end up transferring this code to another person's machine, you're going to have to again enter manually that directory path, which is a massive pain. So that's why this automated way to generate the folder lookup is a really nice way. And if you continue using R, I hope you remember that there's at least one useful thing you learn from this course, and it's that one-liner just there. Okay, so once you've got the folder, then all you need to do is you need to basically get the name of the file, and you need to join it to the folder path. So here we're using the function file path. It's taking the folder that I just mentioned before, and it's just going to take this file name lc.txt, and it's just going to literally put it on the end of that file path. So if I enter that, you can see that this is written to the console, the folder path plus that individual file name that I mentioned previously. This is what we want to import. Now when we tell R, okay, go there and grab me that piece of data from that file, it's going to just be able to import this straight away, hopefully straight into the global environment. So let's do that, and now we've got LC up here. Okay, so this is actually this is a set of text data representing a raster file for land cover. So just assume that each one of these numbers represents a separate land cover type. So where are we? yeah, so these data roughly resemble raster data or a matrix, but for ease we're just going to use one column here because I don't want to overcomplicate things. So let's just take variable 1, which we do after we've loaded in also the height data. So we've got the land cover data which we've been over, and then we also have for each individual, let's just assume 1 kilometre square, we then have the height associated as well. So if I just flick between these two, we've got the land cover values here, and then we've got the height of that individual 1 kilometre square. So let's just assume that this is the topography. So it's the level of undulation within the landscape, essentially in meters. Let's just assume it's meters. Okay, and then let's just take a single variable and create a data frame from it. So it's saying go into the land cover data and give me variable 1, go into the height data and give me variable 1, create a data frame out of it called new. And that's what we've got here. So land cover variable 1 and height variable 1. Okay. Now what we want to do is to get the population mean from the data frame and just get the height mean, essentially. And it's printing here, so it's about 11.68905 meters on average across that one variable that we've pulled out. And now we're able to just take a sample of, say, 5 draws at each 5 data points at each draw that we have from the variable, if I can speak. So essentially what we're doing here is we're saying go to the new data frame, get the height column, and then I want you to take a sample, and I want your sample to be 5 data points. So do you see how I'm running this snippet of code and printing the values to the console, and each time it's grabbing as just 5 data points, 5 height data points, and then we're able to essentially take the mean of those 5 data points. So 14, 13, 10, 13, 10, 12, 8, 15, 12, 10. So there's quite a bit of variability. So now we're able to take a random sample of 50 and calculate a 95% confidence interval. So let's sample the height variable with, let's take 50 data points at each time. So it's basically is the same function again, but this time it's spitting out 50 individual data points from the population. And let's assign it to SH. And then let's take, so it's a sample height, that's what SH stands for. Then let's assign X bar, which is the mean of SH. So when we do that, we get 10.5 in this instance. So let's assign it to X bar. Then let's take the standard deviation using the built-in standard deviation function for SH, which is 7.690251. And let's take the length and assign it to n, which essentially is 50. So once we've done that, then we're able to get the z value for the 95% confidence interval on the upper part of the distribution. So we're using 0.975. 0.975, yep, that's correct. And that produces that same value as before, so the 1.96. That gives us our z value. Then let's take the standard error, so the standard deviation over the square root of n, which here is about 1.08. And then let's multiply them together to get the SE value, which I've now assigned to the global environment up here. So now we can estimate the lower and the upper bound as we've done before. So for the lower bound, we need to subtract the error margin from the mean. So here we're going to subtract it and produce this value, 8.37721. And then here we're going to get the upper bound. So we need to add it to the existing mean value, which is 12.64039. And we're able to plot this. So we have the sample height values on the x-axis from 0 up to 40, and we have the frequency of those values all the way up to about 14. And we're able to plot the x-bar, so the mean value that we got. We're then able to plot the lower confidence bound in blue, and then we're able to plot the upper confidence bound in blue as well. And that provides us with the confidence interval around the mean value. Okay, so we're 95% sure the population mean lies within these particular values. Okay, so let's create a distribution of the sample means and make a histogram. So here it's just set up so we create an empty vector for the sample, and then we go through the for loop again, which we've covered many times, and we're going to, I is going to take the value of 1 all the way up to 10, and for each time that it iterates through this loop and takes a value, it's going to place the result of this, this sample mean into the SAM vector based on the row index. So remember I told you before, for iteration 1, when I is 1, it's going to place it into row number 1 in the SAM vector. Okay, I showed you before in the Excel spreadsheet. So if that's not clear, then we can show that again now. So it's just one example. Let's take these 3 numbers. And what's going to happen is for iteration 1, when we have row 1, it's going to say, go into row 1 and place in my first value, which is 7.115. And then for row 2, let's go in and place that next mean value, which is 14.698. And then for row 3, go in and place my third value, which is 10.86. And so on and so forth, okay? All the way up to, in this case, 10. And each time it's going to be taking 10 data points. So it's just taking 10 of them from the population data set, and it's taking the mean of those. Okay, so you can see how I'm iterating through them here. And then it's going to take the average across all of those values and add it to the vector. So we're going to play with those parameters now, but what I want you to do is I want to pause the video here, please, and I want you to just spend 5 to 10 minutes, and I'd quite like you to run through this vector, either printing this data to the console or to the environment, but basically plotting it as well to the graphical output here. And I want you to vary the number of times that we iterate through this. So this sequence value here, I want you to change the loop so that it goes for 100, 1,000 and 10,000. I want to observe what happens in the histogram. And then also I want you to change the code so that we sample more data values at each data point. So I want you to change this from 10 to 30 to 50. And each time that you do that, we're going to evaluate what happens over here with the histogram. Okay, so you can see that it's changing a little bit each time that I run it now, but we're basically keeping the number of iterations in the loop and the number of samples each time the same. So it's not really changing too much about the underlying distribution that we end up with. Okay, so please do that now. Okay, great. I hope that you've been able to play with those key parameters and actually understand what's happening in the code, and particularly understand what's happening with the histograms that are generated. So we're just going to run through this now. So essentially, as we start to increase the number of iterations, we start to get a much more recognizable normal distribution shape. So as we take more iterations, this is starting to look like a Gaussian distribution. So you can see me iterating now. We've gone from 10 to 100 to 1,000 to 10,000 samples, and we can see that they're normally distributed. But the mean is starting it is jumping all over the place a bit, and one reason for that is that we only have 10 samples being taken each time. So if we change to taking 30 samples, we would actually get less variation in the estimate each time, because essentially what we're doing is each time we take a draw, the mean is going to have more values to average over, which means that the underlying distribution of the means that we get does not vary quite so much. Okay, and you can see that within the resulting histograms. So that's that exercise completed. Now we're just going to move on to the final one. And the point of this is essentially to create just a fairly rudimentary stratified sample. So let's assume that we have all these different land cover types. So that might be grassland, that might be forest, it could be mountainous terrain, it could be lake. And essentially each one of these numbers represents one of those types. Okay, so we could look at how many different types of land cover that we have within here, and we could do that by just sorting the data frame. So it's basically going from the lowest number all the way up to the highest number for all those different land cover types. Let's say, for example, that we're only interested in those land cover values which are 22 and 43. Maybe these are one's forest, 22, and 43 is mountains, and this just makes it hard to do anything that we want to do. Let's say that we want to build some infrastructure, we want to roll out energy access, we want to roll out fast broadband. If you have to do it in forest, that might be harder to do because you might have trees in the way to do certain things, if you need to lay power lines, whatever. If you do it in mountains, it might be even harder because you've got to fight with the terrain and you might not have existing infrastructure to build off. So that's why you might want to pick out these particular land use cover types. So let's just get some of those key metrics that we might be interested in. So we'd quite like to get the number of times that land use cover type occurs. So here we're saying, get me the land cover type 22. And then essentially, I'm not sure if this will run. All right, so when I say, when I do this, what it's saying is each one of these data values equal to land type 22? And it's saying either true, false, true, false. And then essentially when we do this, it subsets all those values that are true. So it's saying if it's a land cover type 22, then give me the height, return me the height. So we have all of these different heights for those land cover types that equal the desired value 22. And then we're able to essentially get the length for that, which is 55. And then for all of the height values as well, what we could do is we could take the mean. So again, this is saying, give me all of the values that equal 22 in the land cover type, and it's going to be true or false. And then it says subset those heights that are equal to 22. Okay, and then when we've got that, we're going to take the mean value. So that's fairly straightforward, I hope. We're going to repeat that for land cover type 43, as you can see here. Now when we've got those, we want to carry out some proportional sampling. So let's say that we want to take 20 samples, and we want the sample to be stratified based on 10% from land cover type 43, and therefore that means 90% from land cover type 22. So how do we do that? Well, we know how to segment the values that we're interested in because we've already been doing it here. So this just produces the binary yes, no, true, false answer for each one of those values as to whether it equals land type 22. And then we're going to, if it's true, get those values which are listed here, for which I think there's 55. I think that was the number that we got previously. Yeah, 55. And then I want you to sample 18 of those. So if we keep sampling 18 like I'm doing at the moment, it's just giving me 18 of those values each time that that fit that requirement of being in land cover type 22. So we can actually show that. So here it's printing all of those values, and it's telling us that it's selected 18 values because I made it print the vector of values and also the length. That means, however, that we also need to add in those values which meet land cover type 43, which we wanted 10% of. So obviously I didn't cover this before, but we used 18 as the sample because 90% of 20 is 18, and that's why. So the complement of that, if we want 10% of 20, it's obviously going to be 2. So that's why down here what we're doing is we're sampling just 2 values each time from those land cover types which meet for the height for the land cover types which meet 43. Okay, so I hope that's clear to you. I'm just running it now so that you can see each time Ed presses Control Enter, it's taking 2 random samples from that land cover type 43, returning the heights. So we're getting 35 and 18 quite often. And what we're able to do is, as we've already added this stratified sample to the environment up here, we've got 18 values, we're able just to append that vector by adding the 2 new values on the end of it. So let's see if we can do that now. So we've added it to the stratified sample. We now have 20 data values in here, which is great. Now let's print that. So essentially these first 18 values were from the land cover type 22, and these last 2 values were from the land cover type 43. If 43 was mountains, then maybe that would make sense because these have higher values here, so maybe they've gone up the landscape slightly more. And then for the whole number of values that we have in our sample, we have 20, which was our aim, to take 20 samples. Okay, so I hope that that's clear. Run the code. If it's not clear when you just click enter, make sure you kind of do what I've been doing, which is you just highlight the specific part of the line that maybe isn't clear. I always remember learning to read, and my dad would take the large words and he would break it down into syllables and say, like, remember you need to pronounce each one of these syllables, and if you can't pronounce the full word, you need to break it down to smaller bits. And I feel a little bit like running these code snippets where you have one-liners which do quite a lot of different things. This is how you should approach it. If it's not clear when you've got this one big horrible line of code, just break it down, because you'll realize that it's just a sequence of smaller, quite easy to understand logical steps of processing the data, basically. Okay, great. Well, that is the 5th lab. Now you've had the 7th lecture as well. I'm going to be setting a test for you to cover this material, and there's also going to be the assignment which I'm going to be setting today and which will be due a week today. If you've got any queries about any of this, don't hesitate to reach out. I hope you do well on the exam. Good luck with that. And then hopefully you'll get some time off at the weekend as well to have some wind down time before we start again, trying to push the remaining assignment work forward over the next couple of weeks. Okay, thank you very much, and I'll speak to you all soon. Goodbye.